Hi everyone, my name is Alexis Osmond, and this is a space-based characterization of a quarter-billion-star photometric catalog. First, a few acknowledgments, including the BDBS principal investigator Michael Rich and the person who did most of the data reduction, Christian Johnson. The formation and history of the bulge of the Milky Way galaxy remains a mystery. However, very large datasets at all wavebands are leading to new discoveries impossible just a few years ago. For example, these two figures show galaxies with X structures rising out of the plane. The prominent X shape in our own galaxy was only discovered in 2010. This shows that the bulge is complex and still has surprises in store. The Blanco DECCAM Bulge Survey is currently the largest ground-based imaging survey of the inner Milky Way bulge at visible wavelengths. The goal of producing a uniform wide-color survey of the southern galactic bulge is to disentangle the formation history of the inner Milky Way through measurement of star positions, motions, and chemical abundances. On the right in yellow is the fully reduced and calibrated BDBS footprint superimposed onto a map of the Milky Way. To emphasize the challenge of this work, we can look at a subregion of this image, which presents a better view of the density of objects in just half of a degree in the full image. If we zoom in closer, a 7/100th of a degree width subregion gives an even more accurate depiction of the challenge presented when working with a quarter-billion star catalog. At the faint end of apparent magnitude, the number of detections drops off as a result of source faintness and source confusion. This is another image depicting a crowded half by quarter degree field captured by BDBS over a 71-degree image of the Milky Way. The second Gaia data release provides a space-based astrometric reference catalog, but to less great depth than BDBS. Thus, Gaia DR2 allows us to both characterize and calibrate residual astrometric systematics in BDBS, while allowing us to demonstrate the degree to which our seeing limited ground-based data extend and complement the sample probed by Gaia DR2. My goal was to cross-match BDBS objects onto Gaia for accurate photometry and astrometry. To do this, I used a subregion cut out with LSD as a prototype for mappings from BDBS onto Gaia with TopCat. Using LSD in this way treats a multi-terabyte dataset as just another Python table. Astrometric and photometric systematics were characterized as a function of apparent magnitude and location on the detector, and then I automated this analysis with Python. In TopCat, I was searching for systematics such as positional offsets and false detections, and I used Python to run spot checks on the BDBS photometry and astrometry. When initially exploring TopCat, I began with this prototype region with a field of view 1 degree in diameter, which clearly isn't super helpful with analysis in this format. With a closer look at the red marks as BDBS data and the blue marks as Gaia DR2 data, I was looking for good matches. Zooming in further, matches and mismatches become more visible. With the help of Simbad and Aladdin Light, I was able to enter coordinates and view that point in the sky from various telescopic perspectives. This helped me see a real-life image of the data point seen in the last slide. After using Aladdin Light for the figure on the right, I was able to determine the clumping of stars in the left figure is due to a routine trying to detect a very bright object, so the cluster of secondary detections is an artifact of the finding process. CCD saturation also plays a part in confusing the detection algorithm, leading to multiple detections. The diffraction spikes are caused by the telescope structure holding the secondary mirror up, causing the spikes to be aligned differently in the two figures. A good match between BDBS and Gaia is defined as a Gaia point within 0.45 arcseconds of the corresponding BDBS point. Referring back to the 7/100th degree width image, you can see that the field is extremely crowded, which can lead to bad matches or mismatches. In these figures, the further away a point is from the central dark region, the greater the possibility for a mismatch. The data appears to be shifted above the x-axis due to a non-zero average right ascension and declination offset. This indicates that the pointing we'll see in a moment isn't quite right at the level of the offset. This is also where the decision was made to clip points outside the 14 to 18 magnitude range to remove outliers, bad matches, or mismatches. This subset vector plot shows that the median offset in position is obvious, showing a general direction of motion pointing to the upper right corner. When this offset is subtracted, the residuals do not show obvious flow patterns, suggesting the low-level distortion removal that was done as part of BDBS analysis is not too bad. Were there to be residual distortion, rotation, or shear, then there would be a clear pattern in these arrows. Consistent with this, the marginal plots also don't show much evidence for flow, although there appears to possibly be small-scale offsets, potentially an artifact of low-number statistics causing some of the cells in the averaging to jump. Here, vector plots showing the flow of the entire field of view, not just the 14 to 18 magnitude range, is consistent with the flow direction of the select region from before. Still, the left plot has no uniform motion. Marginal plots again do not show much evidence for flow. There appears to possibly be small-scale offsets still, but less dramatic than in the previous subset. Astrometric bulk offset is on the order of 0.025 milliarcseconds at this point. Focusing on this astrometric offset, subtracting the median in the left figure still leaves some minor visible distortion seen in the figure on the right. Now looking at the full set of objects, the top row shows 80% of the total objects with their positional offsets, and the bottom row shows 20% of the objects after subtracting the positional offsets. Shown in the two figures on the right, the subtraction of the positional offset in the bottom figure makes a significant difference in the visible distortion pattern in the top figure. The top two histograms show the offsets in RA and DEC of the training sample in gray and the test sample in blue. The bottom histogram shows the position angles of the training and test samples. To address uncertainty, the left histogram shows the square root of the standard deviation in RA and DEC with the y-axis on a log scale. It shows that the uncertainty post-correction is on the order of 1 milliarcsecond. The histogram on the right shows the length of the median offset of the training sample and the test sample, which has a significantly smaller uncertainty with the horizontal axis on a log scale. In December 2020, Gaia Early Data Release 3 was made public. Since then, we've been able to apply the previous correction when mapping BDBS onto Gaia EDR3, as shown in the pre- and post-correction figures on the right. Finally, zooming in shows a similar repeating pattern in the Gaia EDR3 mapping as seen in the Gaia DR2 mapping. Post-correction, the bottom figure lacks a distortion pattern even with its arrows being magnified by a factor of 5. The histograms show the difference in right ascension and declination between the two datasets before the correction in blue and after the correction in red. In both cases, the root mean square residual lengths have shrunk, meaning the applied correction successfully reduced the visible astrometric distortion pattern. In conclusion, there is apparent static distortion at the 60 milliarcsecond level, and subtracting it largely removes the coherent pattern. The formal uncertainty introduced through the correction is on the order of 1 milliarcsecond. In terms of future work, the about 10 billion individual measurements covering 250 million stars towards the inner Milky Way make BDBS an excellent pathfinder for future large-scale surveys such as LSST, and will be useful for a wide range of galactic studies. We intend to apply the correction to the entire catalog so that when the catalog is released, it has astrometry to the best of our abilities to support a wide range of investigations by the astronomical community.